Okay. Okay, welcome everybody to this second day of the LMS-Bath Symposium on the mathematics of machine learning. My name is Elena Celledoni, and I'm going to chair this first session for the second day. And it is my pleasure to introduce the first speaker today, who is Coralia Cartis from the University of Oxford. And she's going to talk about dimensionality reduction techniques for large-scale optimization problems. Please, Coralia.
Thank you very much. I would like to thank the organizers for this very nice invitation and opportunity, and for all their efforts to put this event together online. I know these things take a huge amount of time, so thank you for bringing, the community together at this time. And I would like next to mention my co-authors. So various parts of this work are done together with my postdocs, Yari Fox and Estelle Massar, and my PhD students, Adilet Otemisov and Zhen Shao, my former PhD student, currently research fellow, Lyndon Roberts, and our collaborator at NAG, Jan Fiala. So today I will talk about sketching, and I will begin with just thinking about, just reviewing what is sketching, and then I will talk about its uses for optimization within optimization algorithms to try to improve the scalability of optimization algorithms. So just to remind you, if we have a given data matrix A, n times d, so overdetermined, n larger than d, and some epsilon s is 0, 1, S is called a subspace embedding for A if it preserves the length of vectors in the column space of A. So it projects the vectors in the column space of A essentially correctly. What we have is the well-known Johnson-Lindenstrauss lemma that says that if S is a scaled Gaussian, where the size of S, the number of rows, is proportional to D, the small dimension, then S is a subspace embedding for A. So scaled Gaussian matrices provide a subspace embedding with probability 1 minus delta. And given that M here depends on log of delta, this is actually a high probability result. However, it's expensive to form S times A when S is Gaussian because it's dense. So people have looked at sparse embeddings. And what is the simplest sparse embedding, of course, is uniform sampling. So uniformly sampling rows of A and forming SA by just a subselection of the rows of A. However, the problem with that is that you may miss an important row. If there are rows that are more important than others, this has a positive probability of missing it. However, when A has low coherence, sampling does provide the subspace embedding. So what is coherence? Coherence measures the importance of rows, essentially. So given SVD, sorry, this V should be V transpose, given the SVD of A, we call the leverage score the row norm of U, of a row of U. And then the coherence of A is the maximum of all these row norms of the matrix U. So we can interpret this as, so if the coherence is small, then the rows are similar in magnitude, similarly important. And so we can see that then we have some hope of showing that sampling provides a subspace embedding. However, so the result is that the size of S is proportional to the coherence of A and D log D. Okay, that's for sampling. What other kind of better sparse embeddings do we have? Well, sampling is a matrix with 1 non-zero per row, but hashing matrices have 1 non-zero per column. And when we apply a hashing matrix S to A, we then touch all the rows of A. So it's a better sketching matrix because it will not miss important rows. So we expect this to be more robust. What can we say for hashing in terms of their subspace embedding properties? And this is where we have a contribution. So Meng and Mahoney showed that without any requirement on the coherence, one can give a subspace embedding property for a hashing matrix with one non-zero per column, and it's proportional. The size of S is then proportional to D squared. However, there is here as well a connection to the coherence of A, and Bourgain and others showed that if the coherence is less than 1 over log to power 3 of D, then again, hashing provides a subspace embedding for when the size of S is proportional to D log squared D. And what we were able to do is to reduce that size of S to D, to the optimal value D, but we had to kind of relax, to tighten a little bit the condition on the coherence of A. So the coherence is now less than 1 over D, but then we can gain some in the size of S. The size of S has direct implications on the computation because it's what you're going to use in the algorithm. Okay. How about if one has more than one non-zero pair columns where in hashing? Well, you can, and then the robustness improves further. And we were able to show that if you have a sketching matrix with S non-zeros, then you can embed correctly matrices with coherence less than a given value times square root of S. So the coherence requirement relaxes by square root of S. And numerically, what you observe with S hashing is that when the matrix A is very sparse, then using more than one non-zero per column is observably beneficial. And we have quite extensive numerical experiments for that. So this was just a brief kind of overview of what is out there for sketching a matrix. And now I want to go on to talking about how to use these kind of ideas inside optimization algorithm to improve their scalability. Okay, so there is a direct use for linearly squares, but I will not talk about it here. So I want to talk about non-linearly squares problems. And what I will talk about is sketching in the observational domain, also called sum sampling or batch methods. So we are going to basically try to reduce the number of observations or measurements or data points that we use. And I will talk about that in the context of derivative-based and derivative-free Gauss-Newton methods. And then I will talk about sketching in the variable domain, essentially subspace methods, randomized subspace methods, block coordinates or subspace, for, again, Gauss-Newton derivative-based and derivative-free, and hopefully also about a special class of methods, a special class of problems and global optimization. Okay, so let us begin this journey. So first I will talk about derivative-based methods, then derivative-free, and then hopefully global optimization. All right, so Gauss-Newton methods for nonlinearly squares, the bedrock of really the most successful method for solving nonlinearly squares problems. So we have a function f that's a sum of squares of residual terms Ri. So R goes from Rd to Rn. We can address underdetermined and the overdetermined R, but maybe it's simpler to just think about the overdetermined case. So R goes from Rd to Rn. So we have n terms, n observational terms, and x lies in Rd. And we have J is the Jacobian, the n times d Jacobian matrix of first derivatives of Ri. So Gauss-Newton applied to minimizing f at every iterate xk calculates a direction sk by minimizing approximatively this linear least squares problem here with some regularization and so on that I'll mention in a moment, or trust region or line search. So So basically the core local model that we approximately solve on each iteration is this linearly square, where at xk here, so inside the norm, what do we have? We have the linearization around xk of the nonlinear residual function r. Okay, so if we expand this linearly squares problem, we get a quadratic local model that's convex, and that has here this J transpose J term. That's a subpart of the Hessian of f, of the second derivative matrix of f, but it's not the full Hessian, so it's an approximate Hessian. And in the first order term, this J transpose R is nothing but the exact gradient. So this model here matches the gradient of f correctly. So it's a correct first order model and an approximate second order model. And it's convex, so it's a nice model. And to calculate it, you only need the first derivatives of R and R values. You don't need second derivatives. Okay. But you get second derivative information about f. Okay. So in the algorithms, this model has to be, you have to do a bit more than just minimizing this model to get the next guess of the solution. You have to you have to control the length of the step that you calculate sk, either by line search or trust region or regularization. So first, I want to talk about how to sketch in the observational domain. So what to do to reduce this n here. That's the first thing I'm going to talk about. So for this, I'm actually just going to apply an existing stochastic trust region method to the Gauss-Newton model, okay, to nonlinearly squares and the Gauss-Newton model. So there is a paper, there are a few papers on this algorithm called STORM. I recently found out there are many optimization algorithms called STORM. This is a stochastic trust region method, and we are going to apply it to this model here. So what we have is that for some approximate jk and rk, we are going to solve this model, linearly squares, subject to the trust region. And gk is now this approximate gradient, okay? Then we are going to draw estimates of the nonlinearly squares function independently of the model that we had before and measure progress. So we are going to measure this rho that looks at whether the estimates go up or down. The change in f, the estimated change in f, improves when we have minimized this model, this trust region model. So fk minus qk will be positive. We do minimize the model, and then we want to measure if the function is positive, the function decrease is positive, and it's a multiple of this model decrease. If that's the case, then we take the step and maybe increase the trust region radius so that we look in a larger region. And we also have to be careful that the approximate gradient is comparable to the size of the trust region. The trust region size, delta k, will be a measure of convergence, as well as constraining the step. So if that's the case, we take the step, otherwise we stay at the same point and maybe shrink the trust region. So we have an adaptive framework. So this delta adapts in the run of the algorithm. And it's actually crucial that it adapts because it gives nice self-correcting properties for the algorithm. Okay, so what condition do we have on this I just wrote there a jk and there rk, and I haven't said at all what conditions it has to satisfy. Well, this approximate gradient has to satisfy a probabilistic linear model condition. So we say that it has to be close to the true gradient in a region of the same size as the trust region ball. Okay, and similar properties for the function in the trust region. Okay, but these only have to hold with a certain probability alpha. Okay, so the gradient is accurate, sufficiently accurate, not exactly accurate, sufficiently accurate with a certain probability alpha, and then the estimates that we use to measure progress also have to be sufficiently accurate with at least a probability beta. Okay. So in that case, right? So they don't have to be unbiased estimates of the gradient. They can be biased, right? And in the algorithm, we won't know at every iteration whether they are correct or not. Okay, so we only know this will hold with a certain probability. Then, if the function, the original function, is sufficiently smooth, so R is smooth, J is smooth in the sense of Lipschitz continuity, then when we apply the storm algorithm to the nonlinear least squares problem, and provided alpha and beta are sufficiently large, then the expected number of iterations for the true gradient to go below epsilon is at most epsilon to -2. So the expected number of iterations is at most epsilon to -2. Epsilon to -2 is the deterministic complexity of Gauss-Newton method with trust region, say. So this matches that complexity of the deterministic case times a constant multiple depending on the probability of the model and the function estimates being sufficiently good. Okay, so I note here that we can allow biased estimates, and we allow that on the iterations where the models are bad, they can be essentially arbitrarily bad, but we still have essentially convergence with probability 1. Okay, so what can we do in the numerical algorithm? So this framework applies to stochastic gradient, to batch methods, to subsampling. You can show that if you apply those kind of methods, so if you do subsampling when you have a sum of functions, like we have here for nonlinear least squares. So if we take enough observational terms proportional to 1 over the size of the trust region radius to some power, then you get a probabilistic model with sufficiently high probability. Okay, so this probabilistic condition turns this probabilistic condition becomes a condition on the batch size in your algorithm. All right. So what we do, in fact, in numerics, we just sketch the linear least squares. So we linearize the model and then we sketch it. But note that we are not going to compute J. We just compute a subset. We just compute. We just sketch it from the left-hand side. So we don't need to have J itself. Okay. We construct this model. Now notice that we lose accurate function information, and so indeed it becomes a stochastic algorithm, but numerically we just choose the size of the sketch to be proportional to D from the embedding properties. The theory does not quite tell us that. The theory that I just presented tells us that this M may need to adapt with delta, okay? But numerically, we notice that size D is enough. And here's a problem from the QTest collection. These are just vanilla implementations of sketching inside the trust region algorithm. And what we see here, so we compare, no sketching is just Gauss-Newton in blue, and then 1 and 2 hashing, and then, it's not coordinates, it's sampling. So sampling is in orange, and it does not work very well because it gives you a bit of improvement, but then it stagnates. Hashing works better. Gauss-Newton is best in terms of iteration, but then when you look at runtime, iteration is a misleading kind of concept. It just counts how many linear least squares you solve. But what you should be looking at with these methods is runtime. And in runtime, we gain with hashing on Gauss-Newton. Okay, so I've talked about how to sketch in the observational domain. So sketch Gauss-Newton in the observational domain. Now, how about if I want to sketch in the variable domain? Okay, so now I want to reduce the size of X. So I keep the same number of observations and we reduce the size of the variables. So we get a randomized subspace method. Okay, so I'm going to draw a sketching matrix S. So now it's of different sizes, P times D. And I'm going to calculate a subspace Jacobian. Okay, so this is my subspace Jacobian. I don't form the Jacobian, I just calculate Jacobian actions. And then I solve this reduced linearized model. So I have a linearly squares now in RP, not in RD. So I solve that, but notice that now the function values are accurate. Okay, we get a stochastic stochastic process, but with accurate function values. So then I solve a linearized, regularized, reduced model with this quadratic regularization or with truss region. Again, like before, we measure progress, but now we have these accurate function values, and we have a very, very standard truss region here. We have no condition on how the model gradient has to be compared to the truss region size. It's just the usual regularization and truss region. You take the step if this row is sufficiently positive, and maybe increase the truss region or shrink regularization. Otherwise, you stay at the same point and do the reverse with the algorithm parameters. Okay, so in this case, because I have accurate function values, the properties are, we need far weaker requirements on the sketch. So all we need is that the length of the sketched reduced gradient is bounded below by a multiple of the true gradient. Okay, and we need a bounded sketching matrix and all these, both these properties with a certain probability. And then and this epsilon s here is like a half. Okay, you don't need it to be close to 1 or anything. Then we can have a high probability result. So the subspace, the randomized subspace Gauss-Newton, takes at most a multiple of epsilon to -2 iterations. And again, we have some terms here depending on the probability of this sketching property holding to generate a sufficiently small true gradient, right, with exponentially high probability. So exponentially high probability, we get essentially a multiple of the complexity of the deterministic case for driving the true gradient below epsilon. Of course, we don't get this, we don't see this true gradient in the algorithm, but we know it happens. So what under what assumption does this sketching accuracy property holds? So when does it hold? For what kind of S matrices? Well, now we go back to the subspace embedding properties I started with. Sorry, I'm not going to talk about the proof. Sorry, I don't have time. So Sk can be a scaled Gaussian matrix with this P. Because I only need to sketch the gradient correctly, I only need a subspace embedding for 1D, a 1D subspace, okay? So I don't have a dimension dependence in the size of S. So S can be small. So in other words, you know, I can have a fixed block size, a fixed value on a fixed P, okay? That's a constant. There is no dimension dependence there. And the same with hashing. So we have nice subspace embedding properties, and we can correctly embed 1D vectors for small size SKs. How about if I want to choose sampling? So SK being a sampling matrix, because I'm sketching from the right-hand side here, just means a coordinate method, a block coordinate method. So if I want to do a block coordinate Gauss-Newton method, which this framework captures, I need to be careful, because block coordinate methods do not give subspace embeddings, but they give in general, but they give a subspace embedding property provided the vector that I'm embedding is somehow uniform in the entries. So under a condition on the problem, I can now get a high probability convergence result for block coordinate Gauss-Newton. So if the gradient is kind of uniform in entries, doesn't have some entries that are very important and others that are not, so it's kind of uniformly in size, the components of the gradient are uniform in size, then we can have such a convergence result for block coordinate methods. And it's kind of intuitive, right? You want to capture sufficiently the gradient in the reduced space. And if you're going to just pick entries of the coordinate entries of the gradient, then if they are not uniform, then you may miss some important ones, right? Okay, these conditions that we have is weaker than probabilistic models. We have a high probability result for block coordinate methods under assumptions on the function. If we want to drop those assumptions and we want to have some guarantees for block coordinates, then you drop the high probability. So you can have a guarantee of convergence for block coordinate Gauss-Newton, but in expectation. The expected value of the gradient can be guaranteed to go below epsilon in order epsilon minus 2 iterations, but not the true gradient. Okay, so I'm skipping here. We have numerical experiments. We have a forthcoming paper and a short paper that's already available as ICML workshop paper. We have some encouraging numerics on, in terms of runtime, again, we gain on logistic regression on 2 data sets. Again, with this kind of reduced subspace methods, we gain. And I'm running out of time soon. Is it okay to take another, a bit more, about 7 minutes or so?
Yes, this is going to be okay, Coralia.
Thank you, thank you. Okay, so I talked about the case when we have derivatives. We may not have them stored in the Jacobian, but we have access to Jacobian actions, a small number of Jacobian actions. But what if I don't have the Jacobian at all and I want to approximate it by interpolation of function values? So this is the context of derivative-free optimization. So we have this kind of model-based trust region, which are state-of-the-art for derivative-free optimization. They are sophisticated codes that extend trust region methods to the regime where you only have access to a small number of estimations of R, of R residual values, so values of the residual and F, okay, but you don't have the Jacobian. So these methods, there are codes that are specialized for nonlinear least squares and that use this kind of Gauss-Newton model, where JK now is in the full, not sketch version, is calculated by interpolation of function values. So values you query R, okay, at values in an interpolation set. So you have your base point xk and another n points, and you assume you have R values at these n plus 1 points, sorry, d plus 1 points, d plus 1 points, d is the size of x, okay? So you have to calculate it. How do you do it? By interpolation of function values, and it's expensive because to calculate J, you have to solve this linear system here. So the matrix here is the directions in the interpolation set. So yi are the points in the interpolation set. And the right-hand side here, you have a matrix of the residual values at the interpolation points. So basically what you do is you factorize once this matrix, this interpolation matrix, but then you have to solve for n right-hand sides. So you have to do forward-backward substitution n times, because that's how many residuals you have. Okay, and that's to calculate J. So what we did is to say that one option is to just when you sketch in the observational domain, is to just solve order D of these right-hand sides. So that corresponds to sketching in the observational domain. So I'm not going to construct the whole J. I'm just going to construct a reduced Jacobian by just solving for D right-hand sides. Okay, this leads to a method that's linear in D. Okay, a derivative-free method that's linear in D. And I draw your attention here to this right-hand side plot where we ran MNIST. And in blue, we have no sketching, meaning Gauss-Newton, derivative-free Gauss-Newton. And we managed with this kind of sketching to beat, to low accuracy solutions, to beat the derivative-free Gauss-Newton. Because we don't have to solve for so many right-hand sides, we have a linear cost in D. Okay. All right, so that's sketching in the observational domain in this derivative-free Gauss-Newton. Now, in the derivative-free Gauss-Newton, we also looked extensively at sketching in the variable domain. And then we also reduce the size of the interpolation set. So we have a subspace Gauss-Newton method, derivative-free Gauss-Newton method. We query the point, we query R less times, a smaller interpolation set. And I'm really running out of time. The challenge there is to move out of the subspace. So at every iteration now, you're in a subspace. Your interpolation set is in a subspace. You solve the model in a subspace. But then to get the solution of your original problem, you have to move out of that subspace. So you have to add orthogonal direction, random orthogonal directions to the subspace. But this is the derivative-free framework. So we have to be very careful with our evaluations. We don't want to be excessive in the number of evaluations of R. That's really very much a remit of the derivative-free framework. So we have to be very careful how many points we add. We always keep the size of the interpolation set to P. So we have to drop some points in the subspace and append some more points, while minimizing the number of queries to evaluations of R. So we have a heuristic approach that works well. So again, we have code. And again, what we gain is runtime. And we gain this kind of performance where, you know, the full dimensional version of Gauss-Newton has not moved a bit, you know, has not done one iteration, while these subspace methods have already progressed some. So these, I would say, these regimes are very much for problems where you can't run, say, one full iteration of the method at all. So then you may want to go to this, or you want low accuracy and while minimizing evaluation counts. I really won't have time for global optimization, but I want to tell you that what I've spent and with Adilette and Estelle, and we are finalizing quite a bunch of work now, is to look at global optimization of special structure functions, non-convex functions that are invariant in a subspace. So they only vary along a certain linear subspace that's unknown. So can you globally optimize these functions efficiently without learning the subspace? And what we did is to look at random embeddings. So randomized subspace methods for global optimization of these structure functions. And we looked at theory and numerics, and we have one paper posted and one upcoming shortly, but also a summary paper in an ICML workshop. So I will stop here. If people want to know more about this, I can say in the question time a bit more, but I will stop for now. Thank you for your attention.